Good day, everyone. And once again, we're back together. And today we'll be looking at forces in equilibrium. All right, so if you haven't subscribed, just please do the right thing. Okay, just hit that subscribe button and hit that notification bell as well. And of course, you are more than welcome to like and share at the end of this lesson. If you really like this lesson, please do share it with others. And of course, you can get in touch with us. Our website, mlungisinkosi.co.za, and our email address info@mlungisinkosi.co.za. All right, so I want us to get right into it. Okay, and first of all, talk about what the equilibrium of forces actually mean, right? So when we say that forces are at equilibrium, well, in this case, it means that the resultant in that case simply is equal to zero, right? So those forces are balanced, so the resultant is zero, or it simply means that those forces are simply balanced. Okay, so they are balanced. Okay, and what that simply means, when we look at Newton's laws, which we're going to talk about at a later stage, is that it means that there is no acceleration. I want you to note that. So there is no acceleration. Okay, or you can simply say there is zero acceleration. So in the absence of a resultant, in that case, it means that there's no acceleration, right? So what does that mean? It means either the object will remain at rest, okay? So it means that either the object will be at rest, or in this case, it will be at constant motion, right? So it will be in constant motion. So that means that you will have constant velocity in that case. So let's just reverse engineer the process, right? So it means once we say, or once we talk about constant velocity, right, it simply means there is zero acceleration. And what that simply means, it means that there is zero resultant force, right? So that's what we mean when we talk about forces at equilibrium, right? So what I want us to quickly look at is, what do we mean when we talk about, the equilibrium of forces from a practical perspective, right? So let's just take a scenario where we've got forces. In this case, let's say we've got force F1 acting together with force F2. I'm just making an example, right? So force F2, there we have it there. So what would happen? Okay, let me just draw it over this side. Let me just write it over this side. What would normally happen in this case is that, well, we can find out what the resultant is in this case, right? And how do we do so? We said, well, we can either apply the head-to-tail method, right? I'm going to, or we can apply the parallelogram method, right? So this is a tail-to-tail diagram. So we're going to use the parallelogram method in this case. So what I'm going to do is, okay, let's just make just a little bit of an adjustment here. Okay, so I'm going to try and draw a parallelogram, right? So yeah, I know it's not exactly the best, but you get the point, right? So there's our parallelogram. And then what we would try to do is have a resultant. And in this case, said when you draw that resultant, it will be on from the one corner of your real sides to, the red side to the other corner. So in this case, this would be your resultant. Okay, right. Now, in this case, it means that the object will probably move in the direction of the resultant force, that green, force over there, right? But what if we didn't want the object to move, right? What if we wanted it to be at equilibrium? Then what we're going to do is introduce what we call an equilibriant, right? What is an equilibriant? Well, an equilibriant is a single force that has the same magnitude as a resultant, but in the opposite direction. Okay, so what we would do, I'm going to draw it in black. I am going to now have an equilibrium. Now remember, there was force F1 and F2 acting on this object, causing it to move in the direction of that resultant force, right? But if I didn't want it to move, then I'm going to introduce an equilibriant in this case, and the equilibriant has an equal magnitude to the resultant force, but in this case it is in the opposite direction. Okay, so in this particular case, this would be our equilibriant, right? So equilibrium, right? There's an equilibriant in that. In this case, it causes the system to be at equilibrium, right? Now, I'm going to talk about a law that we're going to use whenever we've got forces that are at equilibrium, right? Well, the law simply says, if we've got three forces that are at equilibrium, okay, so this is the triangular law of forces in equilibrium. This is triangular law of forces in equilibrium. And it simply says, okay, forces in equilibrium, all right? And that law simply says, if we've got three forces that are at equilibrium, those forces can be represented by a triangle, all right, with each side taken in order of its magnitude and direction, all right? So if we've got three forces that are at equilibrium, in this case, they can be represented by a triangle, okay, with each side represented by the different sides of that triangle. All right, let's make an example, okay? So suppose we've got a pot plant, okay, and I'm going to, right, I really suck at drawing, right? Here we are, we've got a pot plant. Okay, so what we're going to do is, let's just say we've got different sides to a wall. All right, so we are going to take the one side. Okay, so let's say we're going to fasten this to the one side of a wall, and the other side, let's just say it's going to be attached to the other side of this wall. Right? Now, how many forces do we have in there, right? So let's say this is rope 1, okay? And let's say this is rope 2, okay? So how many forces do we have at, in that particular case? Well, let's try and draw the triangular, or rather, let's try and see how many forces we'd have. If we can draw a free body diagram, right, showing the forces that are acting here, well, first of all, there would be the force that is exerted by rope 1. So that would be the force on rope 1, okay? But we also know that there'd be another force exerted by rope 2 in that direction, okay? So there's rope 2 there, right? But in this case, remember that this thing is hoisted up, okay? So meaning it's suspended, and therefore it means that there would be an additional force that is the force of gravity, or in that case, we usually call it the weight of the object, okay? So there it is there. Now, in this case, let's just say for argument's sake, we have, an angle there between that, okay? So let's say we've got a 40-degree angle, right? So now, how can we find out? Okay, so then it means that we can actually just draw a vertical line there, and we show that this is 40 degrees in there, right? Now, I want us to do the following. I want us to apply the principle of, the triangular law of forces in equilibrium. Let's just say the bucket, okay, or the flower pot is 10 kilograms heavy, okay? So it has a mass of 10 kilograms, And now what we're going to do is try to find out what is the force on rope 1 as well as the force on rope 2 are respectively. Right. So what are we going to do? We're going to apply the triangular law of forces in equilibrium, right? So remember, this rope, or this bucket rather, is at equilibrium. Why? It is not moving, it is suspended. It means that the forces are at equilibrium, right? So now what we're going to do is let's draw that, let's apply the triangular law of forces in equilibrium, or vectors in equilibrium. So we know, first of all, it will be a head to tail diagram. Okay, so I know the first force that I have, and it doesn't really matter which force you start with. So I'm going to start with the force of gravity. So in that case, we know this is going to be the weight. Okay, so I know this side is going to be the weight. And then secondly, let's draw the force on rope 2. And as I said, it really doesn't matter which one you draw first, right? So remember, the point is to complete a triangle. So there's our force on rope 2. So as a result, there it is there. This is the force on rope 2. Okay, and then we also have the force on rope 1 in this case. So to complete the diagram, there would be the force on rope 1. Okay, right. Okay, so my diagram is really not the best. Okay, so that would be the force on rope 1. Okay, so I'm really trying my best here. Okay, right, you get the point, right? I'm just going to make this, extend this a little bit, and of course extend the other one. So what type of drawing do I have? It should be a head to tail diagram. Okay, right, now please remember that rope 1, right, made an angle of 40 degrees with the vertical, right? So in this case, it would simply mean that there is our 40 degrees there. Remember that weight is a vertical line there, so that means that rope 1 would make an angle of 40 degrees, right? So we've got the force on rope 1, okay, and we've got the force on rope 2 in that case. Right, now, if I asked you, first of all, calculate the following, okay? So first of all, we're going to calculate the weight, okay? And there are just some things that we need to, the force on rope 1, and thirdly, we're going to calculate the force on rope 2, okay? So let's do that quickly, right? So we know in this case that force, or rather the weight and rope 1 create a 90-degree angle there, right? So we know that we're going to have to use, in this case, trig ratios. Why? I have one angle there, okay, and that means that we can apply our trig ratios, right? Now, remember, so the first one, we wanted to find out what the weight is. Remember that weight, please keep this in mind, is mass times the gravitational acceleration. Now, for different purposes, some of you may use 9.8, some use 10. It really doesn't matter. Obviously, depends on your examiner, what they prefer, or your syllabus, right? So the mass, we said, is 10 kilograms multiplied by, I'm going to use 9.8. That's a given that the gravitational acceleration has a value or a magnitude of 9.8 meters per second squared. Please remember that remains constant, right? For as long as we are on Earth, right? Or on the surface of the Earth. So that would be 10 multiplied by 9.8. In this case, that would be 98 newtons, right? So we know the one force. We know what is the magnitude of the weight, and we said in this case, this is simply 98 newtons, right? Now, how can I calculate the force on rope 1. Given that we already know one of the forces, so it means that I know, okay, which are the sides that I have. All right, I want to label those sides. Okay, we know that, in fact, let me do that in green. Right, which side is opposite the angle? This side is opposite. Remember, opposite is directly in front of, right? And then we always call the longer side the hypotenuse. So in this case, this is our hypotenuse. And of course, this is the adjacent side. It's the one next to the angle. Two sides next to the angle, but we've already called this the hypotenuse. So meaning that one is the adjacent side. Meaning, remember, adjacent just simply means next to. Okay, right. So now we're looking for rope 1. So rope 1, in this case, which side of the triangle is it? It's the hypotenuse. But now I'm also going to use a side that I already know, which is the adjacent. So which trig ratio has adjacent and hypotenuse? You remember mnemonic, right? Soka toa, right? Sine is opposite over hypotenuse, cos adjacent over hypotenuse, tan opposite over adjacent, right? So we're looking for hypotenuse as an adjacent, right? A and H, you can see that's going to be the cos, the cosine of angle theta. Now I'm going to say, right, so it means, which means if I'm going to find out about rope 1, I'm going to say the cosine of 40 degrees is equal to opposite, okay, I just want you to, not opposite, rather adjacent, okay, over hypotenuse. So I'm using what I have in this case. So my adjacent side, remember I said that's the weight, this is the side, so that's going to be the weight divided by my hypotenuse is going to be the force on rope 1. Okay, so the force on rope 1, or you can say FR1. Okay, right. So we know this is going to be cos of 40 is equals to weight over rope 1, the force on rope 1. So now let's cross multiply, right? So if I cross multiply, I've got FR1 multiplied by cos 40, the force on rope 1, cos 40 is equal to weight multiplied by 1, that will be equals to the weight, okay? And so I can divide both sides by the cos of 40, okay? That cancels with that. So the force on rope 1 would be the weight, which is, by the way, now I'm substituting. We said that's 98 divided by the cos of 40. Let's see what that gives us. So that's 98 divided by the cos of 40. And we get a force of 127.93 newtons. Okay, so that is how we'll get that. And by the way, you can use scale drawing to try and get that force. In this case, if you haven't watched our video on how to calculate the resultant using scale drawing, please do so and you'll understand what I'm talking about. Now, thirdly, we said let's find out the force on rope 2, right? How would we find the force on rope 2? Okay, let me just use a different color in this case. The force on rope 2 is on the opposite side. And in this case, what do we have? We've got the weight. We already have a value for the weight. So we're going to say opposite over adjacent. Okay? All right? Now I'm avoiding using rope 1 just in case we made a mistake there. Let me rather use information that is given as much as possible, right? So I'm going to say, well, which trig ratio is it? Where's our mnemonic? In this case, soka toa, opposite and adjacent. That's going to be the tangent, okay? So that's going to be 10 of 40 degrees is equals to, right, opposite, that's the force on rope 2 divided by weight, hypotenuse, right? Adjacent, so divided by the force, rather the weight. I'm not sure why I'm making that terrible mistake now. Okay, right, so that's going to be, remember, 10 is opposite over adjacent, right? So in this case, I had the opposite side there and the adjacent side, or rather I want the opposite side and I've got the adjacent side, right? So I can simply say, well, in this case, we're looking for rope 2, okay? Our weight is 98 newtons, 10 of 40 over 1, right? And we can cross multiply again. The force on rope 2 times 1 when we cross multiply there. So force on rope 2 multiplied by 1 is equal to 98 multiplied by 1040. So that would be 98, the 10 of 40. And so what do we get, right? The 10 of 40 degrees. And in this case, we're going to get 82.23 newtons. Okay. And that is how we would calculate the resultant, or rather the equilibriums, right? And by the way, please note, when we've got the equilibrium of forces, each force becomes an equilibriant, okay? So each one of them becomes an equilibrium, because once you remove one of them, then the system is no longer at equilibrium, okay? So each force acts as an equilibriant, right? Ladies and gents, we will look at how to calculate the equilibrium when we've got two-dimension forces, in this case, meaning that forces that are not, or a triangle that is not exactly a 90-degree triangle. But for now, I want to leave this lesson here, and we're going to pick it up next time. I'll see you guys next time. Please don't forget to subscribe and like, and please continue to follow us, and make sure that you tell as many people as possible. Otherwise, from me, your favorite uncle, I'll see you guys next time. Shap shap.